let's talk about voltage summers. We're going to consider this circuit that was built by a student and understand the important error in wiring that was made here. First, let's look at the simple configuration on the right. We see the voltage summer here with two input voltages. We see the feedback resistor flowing to the negative inverting input. Okay, and we see two input resistors, which I am making equal for simplicity's sake. With this configuration, we have the voltage output formula as so. You see that it's going to be a scaled negative version of the sum of the inputs. Now, we can use two separate power supplies to get V1 and V2. However, we're going to be even more clever, and we're going to take a single power supply, place it inside a voltage divider, and have access to two different voltage levels. To make a voltage divider, you only need series resistors. Those resistors will give you the ratio of the voltages at the node between the two resistors. Now, in order for them to be in series, the current through them has to be relatively equal. Now we're going to say approximately equal. We're going to settle for that because we do have to place a load on this. The load must be at least 10 times larger than the resistors that you're using in your voltage divider. That's because we want to minimize how much current is being leaked out towards the load. My load here is my 10 kilo ohm resistor and the 47 kilo ohm resistor, which is the feedback resistor, right? It is going to allow current to seep through and going to go out into this output circuit here and down to ground. Now, the whole concept is to take this voltage source and spread it across these two resistors so that I can control what voltage is here at the middle. If you do not have the voltage source connected in one loop with the series resistors, you do not have the same voltage division that I am trying to get here. Let's look at what's happening in this circuit. We have a 3-volt source, which is supposed to be our supply here. Now notice that it is connected above the R4 circuit. So ground is here. Then we have the voltage source, negative terminal, that's net 4, connected to the positive terminal of R4, or actually, we won't call it positive and negative just yet because it's meant to be the positive terminal, but in this configuration, it turns out to be different. So now, what are we going to see here? We're going to see the current flowing out of this source through the 10K ohm, doesn't flow through the R4 first, and then follows the circuit into the output circuit through ground. And remember, all the grounds are connected, and then up through R5. Now, this is not the direction I intended the current to flow. So what that means is that at this node, I have to have a lower voltage, which would be a negative voltage, in order for current to flow from the ground up through R5. And if it continues, which it will, to the 3-volt battery, it's going to have to be even more negative when you get to node 4 here. This pin is called node 4 here. So we do not have the result that we intended. As soon as you get to node 4, you will rise 3 volts, but you're not starting at ground. You're actually starting at a negative voltage. Okay? So what's happening is that at this node 5, you may not have 3 volts registering as V2 or V1 rather. You're actually going to have something less because this voltage here is negative. So let's let Multisim tell us what our voltages really are. So here we have Multisim running, and we've attached 2 voltmeters that measuring the node voltages. That means that's the voltage compared to the 0 point, the ground. So If you notice here, this voltage is 2.5 volts, not 3 volts, because it is 2.5 volts higher than the 0 point, than ground. That means that node 4 must be 3 volts lower, okay? And we'll see that that is actually negative 0.48 volts. Notice at the node where I wanted to tap in for V2, I have 0.23 volts, almost a quarter of a volt negative, but it's negative. So that is not what I intended. If you should add these two voltages, you're not going to get the 3 volts plus 1.5 volts, which is what we hope to get in the original configuration. Okay, so make sure you are wiring this up as intended. We're going to rewire it quickly and see what the new voltages are. Now here is the intended configuration. You see your 3 volt source is across the 2 series resistors R4 and R5. And you can tell because the bottom end, the negative terminal of the 3 volt source is connected to the ground, and it is going to be spreading its 3 volts across the entire set of resistors. So now we see the 3 volts at the top node and the 1.45, it's approximately 1/2, right? We knew it was going to be exactly 1/2. Approximately 1/2 of that voltage is at the middle node. Now, when I look at the output of my op amp, I see 5 times the sum, okay, which is what I expect. 47/10 is the ratio, that's about 5. And when you sum these two, 3 plus 1.4, it gives you 4.5. And now we can multiply that by 5, and you see that you're going to be maxing out. Because our supply voltages are at 15 volts, we're not going to be able to get the true value here. All I have to do is reduce my voltage to see that true value, that gain value. Let's do that real quickly. Let's reduce this voltage now to 1 volt, and let's see it happen. Okay, let's turn this on and simulator running. All right, now we see 1.5 volts approximately, the sum of these two nodes. Multiply that by 5, you should get somewhere near 6, somewhere around 6. So I hope you're convinced. Be careful how you wire.